Hello and welcome to the last section on Chapter 10, Forces and Motion for Year 12. So we've laid the groundwork about forces, motion, we've discussed Newton's laws, and now what we're going to do is have a look at motion of connected bodies in relation to pulleys. And a pulley is essentially a circular spinning device which often has a rope or string running through it, or over it I should say, which allows a free movement of the bodies either side of the pulley. So that will make more sense when we see some worked examples with pulleys later on. Before that, we do have some warm-up questions to attempt, so if you could try these please next. So 4 questions for you to try independently before we get started with the main body of the lesson. So the best thing is to pause the video now, try these on your own, and press play to check your answers are correct. Okay, so assuming you've had time to do these now, if not pause it then try. Let's have a look now at the answers to question 1. So question 1, we have a discrete random variable, x, which has this following probability distribution function. So the probability for x takes on the particular value r is kr squared for when r is 1, 2 or 3 and 0 elsewhere. So for part A, all we need to do is to complete the probability mass function table below for the discrete random variable x. So I think this will make more sense to you when we use this kr squared expression in the future ones. So for example, when we have here that r is 1, when r is 1, the probability for x is equal to r is k multiplied by 1 squared, which of course is just k. So I'm just explaining to you where this k has come from in the beginning. They've just used this expression here to generate it. So what we need to do is to do the same thing for when r is 2 and 3. So when r is 2, the probability of x being r, probability of x being 2, is k multiplied by r squared, which is now 2 squared. And obviously 2 squared is 4, so that's 4k. And finally, hopefully you've got the idea now, when r is 3, the probability of the random variable being 3 is k multiplied by 3 squared. 3 squared is 9, so that becomes 9k. Okay, so this is where these values come from. So it all derives from this idea of k multiplied by r squared. So we just take r, square it and multiply it by the k. That's all we've done each time. So we filled in the table, that's part A done. For part B, and to find the value of k, all we need to know now is that the total of all probabilities will add up to 1. This is just a bit of fancy notation. So from r going from 1 to 3, all those probabilities must add up to exactly 1. So in other words, k plus 4k plus 9k has to add up to equal 1. So k plus 4k plus 9k, well k plus 9k is 10k, plus another 4k, that gives us 14k. So we've got 14k equals 1, so therefore k must equal 1 divided by 14, 1/14. And so that's question 1 completed, both part A and part B. So let's now have a look at question 2. So question 2 is a mechanics question. So there's a whole paragraph of information here. So before I even read the whole thing, I'm already thinking, I'm going to put this into a diagram to make it more digestible to me. So what we have here is a light inextensible string connecting 2 particles P and Q of masses 2 and 10 kilograms respectively. So it says it's a horizontal force of magnitude 100 pulling particle Q along a smooth horizontal plane. That's that word horizontal again. So I'm now confident enough to just do a straight line with which to model the surface these particles are on. And as well as that, I'm just going to do a diagram here for the particles. So I'm going to clone that one. So that can be P, this can be Q. And there is a string joining them. So I'll do the string in blue, why not? So this one here, I'm going to label P, and the other one can be Q. So it says a horizontal force of magnitude 100 newtons pulls particle Q along this plane. So there's a force going forwards of size 100 newtons acting on Q. So I'm going to just do that there and call that 100. That's just putting into practice what we've got. So particle Q's been pulled along like so. P and Q experience a constant air resistance of 6 and 13 respectively. So P is 6, Q is 13. Now this is an air resistance, so it's working against the motion. The motion is going this way, to the right, and so these resistances will be working in the opposite direction. So these resistances will be going this way for P, and similarly this way for Q. So that's 6, that's 13. So we're almost done. We're asked here to draw a force diagram with all the forces shown acting on P and Q. So because the motion is horizontally, these are the only forces we need to be bothered about here. Okay, so we don't need to worry about anything else. For example, it says here the plane is smooth, so there's no friction involved. But technically, to complete the force diagram, because it does say all forces, we must always remember that actually, for any object with a mass, there will always be a weight associated with it. And so P, we're told, has a mass of 2. So a force going down on P due to its weight will be 2g. Similarly for Q, because its mass is 10 kilograms, that will have an associated weight of 10g. Not 10 grams and 2 grams, but where g means the gravitational field strength of Earth. And of course, because this surface is supporting both P and Q, there will be a normal reaction force acting from the surface up on both P and Q, equal and opposite to the weight, so that the particles don't fall through the floor or fly up from it. And so as well, there's going to be forces vertically, which cancel the downwards forces, equal and opposite, so that'll be 2g on P, and on Q will be 10g. At this point of the force diagram, we're almost complete now, apart from we need to remember in the string itself connecting P and Q, there's going to be a tension force as well. So if a string is taut, which means tight, with no slacking of it, there's a tension force, and tension always acts away from the object in question. So relative to P, the tension will be going away from it. So we'll do an arrow away from P and call that T. Whereas on Q, we can model the tensions going away from Q, so it'll be the same magnitude as the tension acting from P, but from Q it'll be pulling back on Q, so it'll be the opposite direction. So equal magnitude, opposite direction. So tension is a bizarre force. It acts within the same object, but can act in opposite directions depending on what you're speaking about. And so that's the force diagram complete for question 2. We're going to need this diagram for question 3. So on that note, let's have a look at what question 3 has in store for us. So question 3 is quite simple in terms of what it says. It says use your force diagram from question 2 or otherwise to calculate the acceleration of P and Q. So we need to remind ourselves what the force diagram we had was from before. So here it is. So there's actually 2 different ways we could approach this. So one way is the more direct and, dare I say, simpler way, but I will show another way just because I think it's worth knowing more ways to do any one particular question, so that should you forget one way, hopefully you've got more in your arsenal, just in case you forget one way, you can line another way. So here, I'm just going to box off the bottom for the alternative one. So I'm just going to write here, in fact, alternative. So the first one I'm going to show you is what I'd recommend. Okay, so this is a recommended way first. Okay, so what I'd recommend you do is simply to consider the system as one entire body. So by that I just mean consider it all grouped together. So if we were to do this, we can think of P and Q as just one thing, which I'm going to call PQ. So PQ, which is going to basically mean P and Q combined, would obviously be bigger than both. And if we did that, then it has also the added benefit of allowing us to ignore any internal forces acting within the system. So for example, in between P and Q there's tension forces which are equal and opposite, so these cancel out essentially when we consider the whole thing P and Q combined. So I'm going to call this PQ, because it just means P and Q together. So apart from these tension forces which cancel out, we can now look to think about what the total forces are horizontally. Hopefully you can see here, although there are vertical forces, these will cancel, so it won't affect the motion. The motion and acceleration is going to be purely horizontal. So going this way, the only force driving the system PQ forward is this 100 Newton force. And the forces resisting the motion, we have two of them. We have 6 on P and 13 on Q. So we can combine these into one. So 6 plus 13 means there's a 19 Newton force holding it back. So just to make this as clear as I can, I'm just going to add in here where this 19 is coming from. That 19 is the sum of the 6 and 13 from before. So we're now good to go. We can now apply F equals ma horizontally. So F equals ma applied in the direction to the right. So the overall force going to the right is this 100 minus this 19. So essentially I'm saying it's 81 overall going to the right. So I'll write that underneath. I'm just going to simplify it all in a moment. So this is a resultant force. That'll equal the mass of the system. Well, the mass of PQ is the 2 from P plus the 10 kilograms from Q. So the total mass is 2 plus 10 multiplied by the acceleration of a system, which is what we're wanting to find out. So 2 plus 10 is 12. A is obviously A. So therefore A is going to be 81 over 12. And if we use a calculator for this, 81 divided by 12 gives us 6.75 meters per second squared. Like I said there is an alternative. So what we did here is considered the system as one entire body. We could have, if we wanted, considered P and Q separately. So just thinking about P, so if we just consider P for a moment, I'm going to nab, I can't, never mind. I'm just going to do a little circle for P, and I'll clone that for Q. So what I'm going to say here is we're going to consider these P and Q separately, and then see if we can combine in a moment to get some equations out of each. So just thinking about P. Acting on P, horizontally only, we've got a tension pushing it to the right, which is this T arrow here. So I'm going to draw on the T arrow. Like so. Whereas on Q, which I'm going to consider in a moment, Q has that tension pulling it to the left. And so for Q, the tension's acting the opposite way. Now just thinking about P on its own for a moment, the only thing holding P back is a 6 Newton force. And so we can show that by just adding in an arrow and labelling it 6. So that's all the horizontal forces acting on P, actually. Now it's worth noting that the mass of P is 2 kilograms, so the downward force would be 2g. I'm only writing this in just as a reminder that the mass of P is this 2. So F equals ma, applied horizontally for P, gives us T minus 6 equals the mass of P, which is 2, multiplied by the acceleration of the system, which we're still to find out. Obviously I know we have found it out, but I'm just imagining if we had gone this route, we wouldn't know the acceleration of the system yet. Whereas at Q, holding it back is this tensional force here, and also the resistive force of 13. So I need to also add on 13 for Q. And driving it forward is this 100 Newton force. So for Q, using F equals ma applied to the direction to the right, what we have is 100 minus T minus 13 equals the mass of Q. Well, if you remember what Q's mass is, it's 10 kilograms. So I'm just going to label this 10g. Again, just as a reminder of what its mass is, not so much its weight. So overall force of 100 minus 13 minus T will be equal to the mass of Q, 10, multiplied by the acceleration of a system A. So actually what we have here, if you look, is 2 equations we can solve simultaneously. We don't really want to know T, we're not interested in the tension. If you notice here, I've got a positive T here and negative T there. So if we were to add these equations together, the T's would cancel, and all we'd have on the left would be minus 6 plus 100 plus minus 13. So let's work this out. So minus 6 plus 100 minus 13, that gives us 81. So I have 81, and adding together the right hand side, we've got 2 plus 10, which is 12. So we've got actually exactly what we had before. So therefore, in exactly the same way at this stage, we'd also get that A equals 6.75 meters per second squared. So it's a case of what is your preference. I'd suggest this second one, the alternative, is a bit harder because it involves doing a simultaneous equation and there's more steps, but it's just really nice to know, I believe, if you've forgotten one way, almost always there will be an alternative approach when it comes to maths. Let's now finally have a look at warm-up question 4. So for warm-up question 4, we've got 2 boxes, A and B, of masses 2 and 5 kilograms, respectively. They're stacked on the floor of a lift. A is on top of B. So already what I'm thinking here, a lot of information. I want to draw a diagram for this. Okay, so what I'm going to do here, that's my lift. I'm not the best artist, as you can see. So A is on top of B. So that's going to be my B. And then what I'll do a little diagram for A, which is resting on top of B. Make it a bit smaller, actually. There we go. So A and B, 2 kilograms and 5 kilograms. So that's A. In fact, I'll do it to the other side so it's not in the way of a diagram. So I'll have this as being A, and B is below it. So it says the lift is supported by a light inextensible cable and is ascending. It's going up. Fancy word for going up, with acceleration of 0.2 meters per second. So actually there'd be a force pushing it up. That'll be a tension force, so I'm going to label that T. Also as well, it's accelerating upwards with 0.2 meters per second. So if we know that, again, we may as well label this in. So the acceleration is going that way and has magnitude 0.2 meters per second squared. We asked to find the force exerted by box A on box B. So what we need to do here is label a few extra forces in. So A is 2 kilograms. So A is 2 kilograms. So what I'm going to do for A, just colour that green. Whereas B, oops, wrong colour, I'll do a yellow I think. Whereas B is 5 kilograms. So if I colour code B in yellow, that's going to be, whoops, no. That's what I wanted to do. So we need to think about forces acting on A and B. So obviously acting downwards on B is its own weight. So the weight of B is going to be its mass multiplied by G. So the weight of B will be 5G. The weight of A, again, will be acting upon A. So the weight of A is 2. So acting down on A is a force of 2G. Now again, there's also going to be reaction forces as well. So there'll be a reaction force from B acting back upon A. And so there'll be a normal reaction acting on A from B, which I'm going to call that N for normal reaction force. In the same way, there'll be a normal reaction force from the floor of the lift pushing B up. So I'm not labelling it the same N, because these might not be the same size. In fact, they're not going to be. I'm going to label this one R. At this stage, this might be overkill. We might not have needed to do this, in fact, but I'm just showing you how the forces would be working. So all we're after here is to find the force exerted by box A on box B. So we can now remember Newton's third law. For every action, there's an equal and opposite reaction. And so what I'm saying here is because A and B are only interacting together with the N force, this normal reaction here. So essentially, if B is providing this force of N upon A, then A will exert an equal and opposite force on box B, which will be the same magnitude as N. And so what it says here about finding the force exerted by box A on box B, all we actually need to do is to find this N force, this normal reaction force. So if we consider just box A and box A alone, like I said, this diagram seems to be a bit of overkill really, so I'm just going to consider box A on its own to the side. So obviously there's a normal reaction force pushing it up. That's what we're trying to find essentially. That's N going up. As well as that we have its weight of 2G acting downwards. So if we just isolate box A and consider box A only, we can work out the rest because we know what the acceleration on it is and we know its weight. So if we now apply F equals ma going in the up direction, the overall force going up is n subtract 2g. So n minus 2g is going to be the mass of A, which is 2, don't forget, multiplied by the acceleration of a system, which we've been told is 0.2. So that's going to be 2 multiplied by the acceleration, which is 0.2. So now, with a bit of rearrangement, we can work out what n is. So therefore, n will be 2 multiplied by 0.2, so that's going to be 0.4 essentially, plus 2g, 0.4 plus 2g gives us exactly 20 newtons. And so that's a warm-up done. They took a bit longer than usual, but that should hopefully prepare us for what's in store now. So let's now move forward and have a look at this thing I mentioned earlier, pulleys. What are they? How do they work? How do we solve problems relating to pulleys? Let's now have a look at these pulleys. And the easiest thing is just to go straight in with a worked example, I feel, just explaining what they are. So I'm going to just talk you through how you draw a diagram based off one of these questions. So typically, but not always, there'll be two different masses when a question's about pulleys. So here we've got masses P and Q. They've got masses of 2m and 3m respectively. They are at rest and they're attached to the ends of a light inextensible string. The string passes over a smooth fixed pulley. So I'll draw this on in a moment. So a smooth fixed pulley. What on earth is that? You'll see. So the masses hang with a string taut. And so P, to start off with, is on a smooth horizontal table. So because it's a horizontal table, I'm going to draw this in. So all I need to do here is just draw a table. And it says Q is hanging vertically below the pulley. So there's a vertical drop here, like so. And so you've got Q down here, which is hanging vertically. You've got P on here, on this tabletop. So what we need to do is think about what this pulley is, what does it do, and where would it go? So essentially, this pulley would actually sit at the edge, the very edge of this tabletop, like so. Whereas P would be here, like so. And it's attached with a string taut. So the string will connect these two things together. And likewise, dangling off the edge, like so, will be Q. Okay, so the pulley is actually this thing here. And the string just connects the two particles, P there and Q. We can also label on the weights of the particles. So P has got mass 2m. So this is P. We're told it starts off on top of a table. Whereas Q, which is hanging vertically, has mass 3m. Oops, that was a bit of a mess. Didn't intend to do that. Okay, that's more like it. So we need to just complete this force diagram, really. So acting downwards upon P will be its weight. Its weight will be its mass, which is 2m multiplied by g, so it's well be 2mg. There'll also be a reaction as well, holding it up from the surface. That reaction will be equal and opposite. That will also be 2mg. So Importantly here, we're told about P, but it's currently on a smooth table, so there's no friction. The only thing acting on P is this tension force from the string. So relative to P, obviously tension always acts away from an object, for T is going that way. For Q, we need to add on its weight. Its weight is 3 mg, so that's going to be pulling it towards the earth. And it's acting upwards and away will be the tension. So what we need to do now for part A is to work out the acceleration of each mass. So if we consider particle P, first of all, the acceleration will be purely horizontally. It's not moving in a vertical plane, it's moving in a horizontal direction only. So because this particle Q is obviously heavier than particle P, Q will drag P along with it. So Q will prevail. And so P will be moving to the right. And so the overall force, therefore, will be horizontally and to the right. And in fact, looking at P, the only force moving to the right is just T, the tension. So T equals the mass of P multiplied by the acceleration of each mass. So the mass of P is 2m. The acceleration, which is as yet to be found, we're just going to call A. Now again, because this string is inextensible, the objects are going to be moving together in tandem with the same speeds and the same velocities at each point. It's not a bungee, so if one object is moving at 5 meters per second, the other will be moving at 5 meters per second, and so on. Let's now consider particle Q. Okay, so for Q's motion will be vertically. It'll be falling downwards, so the resultant force must be going downwards. So the resultant force going down will be 3 mg, its weight, minus the T resisting that motion. That's the overall resultant force, which will equal the mass of Q multiplied by the acceleration of Q. The mass of Q is 3m, and the acceleration of the system, again, we're calling A. So we now have two different equations. What can we do with these? Well, we can solve them simultaneously by adding them together. And if we do this, on the left-hand side, we've got a T at the top, minus T on the bottom. So when we add, the T and the minus T will cancel. We'll be left with just 3 mg on the left-hand side. So 3 mg will equal what we get when we add up the right-hand side. So 2ma plus 3ma, that's going to give us 5ma. Now hopefully what you notice is we can divide through by m on both sides. So actually this acceleration is independent of the mass. So therefore, A is just going to be simply the 3g divided by 5. So 3g all over 5. Let's sub in what g is, of course. G is 9.8. So 3 times 9.8 all over 5. That gives us 5.88 meters per second squared. Now B. For B, what we need to do is to find the tension in the string. Well, what we can do here, now we know what A is, we can sub this value for A back into the equation of P. So we can now sub in sub A equals 5.88 into the equation for P. So obviously, the tension is going to be 2 times m times 5.88. So T equals 2m multiplied by 5.88. and that's going to give us answer times 2 essentially. To 3 sig figs, 3 significant figures, 11.8 m. So we can't actually work out as a numerical value what the tension is. That's because with information we're given, we can't work out the mass. And as you can see here, the tension is a function of the mass. The tension relates to the mass in some way, which makes sense really. The heavier the mass, the more the tension will be. So now what we need to do, using these results, we need to consider the force exerted on the pulley by the string itself. Now, what I've mentioned before, and what will always be the case, is tension always acts away from any object in question. And so, if we just map this pulley now, and consider the forces acting on it by the string, then tension always acts away. So you can see here the string will be pulling away from the pulley to the left. So actually that's the wrong colour, never mind. It also pulls down on the pulley vertically. So the pull is the tension, which is going to be the same throughout this string. We can always model the tension for anything inextensible as the same throughout its length. So the tension we just worked out is 11.8 m. But in fact, because that was slightly rounded, I'm going to use the value 11.76 to make sure we don't incur any further rounding mistake. So it's 11.76 m that way, and 11.67 m downwards. And of course, the directions of horizontal and vertical are perpendicular, they're at right angles. So from this, we can construct a force triangle. So we've got 11.76 going to the left, 11.76 going down. So let's just map this out now. Whoops, not like that. And of course 11.76 going down. These directions are perpendicular. That's a right angle. It's 11.76 m, 11.76 m this way. So the force exerted on the pulley by the string is going to be this here, which I'm just going to label F. Now, because these sides are equal and opposite, we could also, if we wanted to, work out the direction of the force. It's going to be 45 degrees below the horizontal, because this is a isosceles triangle with two sides the same. So based off this, the size of the force is going to be 11.76 m squared plus another 11.76 m squared. And so if we have to do this, 11.76 m squared, if I square that, we get this value here, plus another of the same, so multiply that by 2, we'll get 276.5952 m squared, which needs square rooting. 276.5952. So obviously when we square root the m squared, that'll just give us m. So if we square root this answer here, it's about 16.6 m. Again, it's in terms of m. So the heavier these masses, the more force will be exerted on this poor pulley. What a shame. So now we can have a look at question part D. So I'll just overrun slightly with that question, so just section that out there. So part D says we need to have a distance moved by Q in the first 3 seconds, and we need to assume that P does not reach the pulley. So we now know that for object P and the system, the acceleration is 5.88 meters per second squared. So what we'll be able to do here is use SUVAT. And again, SUVAT can be used because this acceleration, we can assume it to be constant because we can assume Q is not going to hit the ground and Q is not going to bang into the pulley. P is not going to bang into the pulley, sorry. So SUVAT we want to work out the distance moved, so that's what we do want to work out. So we want to work out S. It did say in this question as well that P is initially at rest. It does say here that at rest. That means that the initial velocity U is 0. The final velocity we don't know, we're not asked for it, we don't care, so I'm going to just cross out the V because I don't care. The acceleration of the system is 5.88. And the time, we're told it's the first 3 seconds, so we just need 3 here. So what equation of motion does not involve V at all? It's again the old reliable S equals ut plus half at squared. Now because u is 0, ut is 0. So we're just going to have half times acceleration of 5.88 multiplied by t squared, which is 3 squared because the time frame is 3. Bang this into the calculator and see what we get. So 1/2 times 5.88 times 3 squared, we get 26.46, which to 3 significant figures is 26.5 meters. So that's a very, very long table. And that's that one done. Finally, for E, state how you've used the fact that the pulley is smooth in your calculations. Well, because a pulley is smooth, it means that there's no frictional force we need to consider about the pulley, so it just makes it one less thing to worry about. It's one less problem. So in terms of how to word this in a question, something like this might do the trick. So essentially, just there's no need to consider any other resistive forces, or alternatively, this dash, the velocity and acceleration of the system is not affected by the pulley. So this pulley isn't going to muck things up, it's not going to get stuck in any way, so it's all good because this pulley is smooth. So talk about in at the deep end, that was quite a long worked example, but let's carry on. Let's now have a look at worked example 2. So here we are. We've got particles A and B, masses 0.4 and 0.8 kilogram respectively, connected by a light, inextensible string. So again, A lies on a rough table with a smooth pulley which is fixed at the edge. The string passes over the pulley and B hangs freely. So B is hanging and A is on the table. So again, it's a similar sort of setup to question 1. So I'm just going to sketch on here what's sort of going on. So we've got A and B. I'm just going to draw A first. The pulley's here. Also, there's going to be a string involved, keeping it all interconnected. It's not even attached to the pulley, that's terrible. That looks more like it. We've got B hanging freely. Okay, so A has mass 0.4 kilograms. So let's label this in straight away. So if A has mass 0.4 kilograms, then its weight is 0.4 g. whereas B, we're told, has weight 0.8 kilograms. You might be thinking here, obviously, these diagrams take a long time to do. It might be tempting to avoid doing them, but never do. Labelling a diagram carefully and constructing it is never wasted time. In fact, it underpins scoring well at mechanics. Mechanics is hard enough as it is. It's really, really hard if you're doing this without a fully complete informative diagram. So anyhow, that's 0.8 kilograms, so its weight would be 0.8 g. Again, acting on both will be a tension force. So tension that way on A, tension up for B. Now, again, it's not really going to bother the system. For A, the acceleration is going to be horizontally, but we may as well label in the normal reaction force, which will be the same magnitude, opposite direction. It's going to be 0.4 g going up. So that's now pretty well labelled. So first of all, what we need to do is just make sure that we've read this absolutely okay and that there's nothing else missing. So a string passes over a pulley, B hangs freely, the string's taut. It's 0.5 meters from the ground. So actually what we need to do is extend this diagram ever so slightly. Draw in the ground. We need to say, therefore, that B is 5 meters below the ground. What am I talking about? I mean 0.5 meters above the ground. Don't know what's wrong with me today. Please forgive. Okay, so I'm going to do here, just make some more space. It's the trouble trying to get it all on one page so you can still have information. Sometimes it's quite hard to do. So that's 0.5 meters above the ground. So I'm going to label this in 0.5 meters. And as well as that, we're told that A lies on a rough horizontal table and that it's 4.5 meters from the pulley. And so we also need to label in an extra distance, would you believe it, of 4.5 meters from here to here. So that's 4.5. Now, are we nearly done? Give yourself a star prize if you spotted that actually no, we're not. It does say here that A lies on a rough horizontal table. So first alarm bell, if it's a rough table, there will be friction involved. But the question's being quite nice to you because it spells it out for you by saying a frictional force of magnitude 0.08 g opposes the motion of A. So that's actually quite good of a question maker to do that. So what we can do here is add in that force of 0.08 g going against A's motion. So that now is finally pretty well labelled. In fact, that is as much labelling as we should need. So now we can work out the acceleration of the system by considering, in fact, A and B separately. So just considering A, first of all, because B is heavier, B is 0.8 kilograms versus A is 0.4, this system is obviously, it'll go downwards. Okay, so it's going to go down relative to B, A will be pulled across the table to the right. So the overall force on A, the resultant force, will be to the right. So overall to the right, it's going to be T subtract 0.08 g. That'll equal the mass of A multiplied by the acceleration of the system. So that's going to equal 0.4a. Whereas for B, the overall resultant force which will act down, the downwards force will prevail, that's 0.8 G minus T. So that will equal the mass of B multiplied by the acceleration of B. The mass of B is 0.8, the acceleration is A. So now what we can do is we can combine these two together and add them. If we add these two and treat them as simultaneous equations, then the T, the tension, will cancel. T here minus T there, that cancels. So on the left we've got 0.8 G plus minus 0.08 G. That will leave us with 0.72 G. So 0.72 G, that'll equal 0.4A plus another 0.8, that's going to be 1.2 A. So therefore A will be 0.72 G divided by 1.2. So it's calculator time. So 0.72 G means 0.72 multiplied by 9.8, that's what G is. We divide that by 1.2, and that gives us 5.88 meters per second squared. Part B, the time taken for B to reach the ground. Well, this one actually is a fairly straightforward see that type question. So when B reaches the ground, it will have travelled 0.5 meters, so the displacement's 0.5. It does say as well, if we read the question carefully, that the system initially is at rest. So initially, therefore, U must be 0, because at rest the starting velocity will be 0. The acceleration of the system we've now established will be 5.88, so B is going to accelerate downwards at 5.88 meters per second. Now, the time is what we're trying to take. The time taken, that's what we're trying to find. The final velocity V, we haven't been told V, but also we're not been told that we need to work it out, so we can leave that alone. So again, what equation could we use which doesn't rely on V? And again it crops up yet again. We can use S equals UT plus half AT squared. So S is 0.5, so we've got 0.5 equals UT. Well, UT is just 0, okay, because the initial speed is 0. So we're going to have half times A, which is 5.88, T squared. So therefore we can calculate T directly. T is going to be the square root of 0.5 divided by half times 5.88. So if we calculate this one, testing how small I can write here. Maybe I'm going for too much on one page, but never mind. So it's the square root of, on the top we've got 0.5, and on the bottom we've just divided everything through by this 1/2 times 5.88. So we get this exact third as a decimal, 0.412 seconds to 3 significant figures. So 0.412 seconds. Now we need to think about part C. Now part C is fairly complex. So it says the total distance travelled by A before it first comes to rest. So let's think of what's going to happen here. So A has got 4.5 metres to go until it gets to the pulley. However, after it travels 0.5 metres along, B will have travelled 0.5 metres down, and the tension will disappear because the string will now become slack because T's hit the ground, T's at rest, there will be no tension left, and so A will just be freewheeling until it stops. Okay, so what we need to do here is think of it like this. So what's going to happen here is A will travel, it's going to travel 0.5 metres along at the same speed as B. So what we can do here, we can find out the final speed of B. I can do that using SUVAT. So, SUVAT, you know the drill by now. This time I want to work out the final speed. So what is the final speed of B? It's going to have a final speed just as it hits the ground after 0.5. It's going to fall 0.5 and hit the ground with some final speed. The initial speed is 0. The acceleration of the system was 5.88 from part A. In this particular case, we don't need to concern ourselves with the time. So from here, which equation doesn't involve T for SUVAT equations? It'd be V squared equals U squared plus 2AS. So therefore V, U is 0, so U squared is nothing. It's going to be 2 times 5.88 times 0.5, all square rooted. So that's what that gives us. So square root of 2 multiplied by 5.88 multiplied by 0.5. We're going to get a value of approximately, well, I'll leave it exact actually so we don't have to round, 7 root 3 over 5. So when A's already travelled 0.5 metres, it will have a speed of this. Then what will happen after that, the string will go slack, the tension disappears, then we need to find the new acceleration of A. So we can write this down, if nothing else for our own mental clarity. So string goes slack, in other words, T disappears. So now what we can work out is the new acceleration of A. So with no tension, A now is going to be held back, it's going to be slowed down by this 0.08 g-force. So now just thinking about A, its velocity is that way, but it's been held back by 0.08 g. So now, F equals ma. Oops, I'll do that in a black colour actually. So F equals ma going horizontally. The overall force is 0.08 g. That's going to equal the acceleration, the new acceleration of A, multiplied by the mass of A. Mass of A is 0.4. Acceleration. So therefore, A new, if you like, let's confuse it with the initial acceleration of 5.88. That's going to be 0.08 g divided by 0.4. Let's work out this is. So 0.08 g, whoops, 2 zeros, 0.08 g, which is 0.08 times 9.8. Divide that by 0.4. We get this here. We get that the new acceleration is going to be 1.96. We could have left that in terms of g, that would have been fine as well. At this point I'm going to throw in the towel. I can't squeeze any more on the page. I'm going to have to scroll down. I'll give up. I'm defeated. So now at this point we can do suvat. So again, the velocity, the motion of A is still going to the right. So this acceleration, I'm going to put it as minus 1.96 because it's actually a deceleration. It's slowing A down. I want to work out the total distance, so I'm going to leave that as S. The initial speed when the string goes slack is actually 7 root 3 over 5. 7 root 3 over 5. When it comes to rest, the final speed will be 0. And again, we're not particularly bothered with t, so I'm just going to say for t, I can cross that off. So what formula doesn't involve t? Again, we can use v squared equals u squared plus 2as. So therefore, S is going to be v squared minus u squared over 2a. V squared is 0, so it's going to be minus u squared. So it's going to be minus 7 root 3 over 5 squared. Divided by 2a, which is 2 times minus 1.96. So if we work this out now, so it's going to be minus 7 root 3 over 5 squared, all divided by 2 multiplied by minus 1.96. That comes out of 3 over 2, which is exactly 1.5 meters. So there's 2 different parts to this. I hope you can appreciate that. So one part is it travels 0.5 meters along, then the string goes slack, then it goes another 1.5 meters before it comes to rest. So what's going to happen here is the total distance it's travelling is going to be 0.5 plus 1.5. So therefore total distance travelled by A is 0.5 meters when it's moving with B. Then B hits the ground, tension disappears, and then it's slowed down to rest by 0.08 g. At this point, we worked out the displacement it travels after B has hit the ground, and that displacement s was 1.5. So 0.5 plus a further 1.5, the total distance it travels before coming to rest is 2 meters. That's some hard going. Let's have a look at just one more, and then you need to try some of these yourselves. So let's finish off now with a final worked example. So here it is, the final example. So importantly, I know it's almost going to be second nature now to think of g as being 9.8, but always read the question carefully. It does say let g be modelled as 10 meters per second in this question. So if you don't follow that instruction, you'd be liable to lose marks. As harsh as that sounds, 10 meters per second, you need to follow it carefully. So reading here, luckily now we have a diagram to help, which is always a bonus. It's got a ball of mass 0.2 kilograms, and that's P, and so P is 0.2. So we may as well just add this in, I suppose. It's attached on the end of a light inextensible rope, fairly standard. It passes over a smooth pulley, which is this here, and it's fixed on the edge of the table. We've also been told that the total resistance to the motion of P is modelled as having a constant magnitude of 1.5 newtons. So we can add in here a force on P holding it back of size 1.5. So what else can we add on? So it says the other end of a rope is attached to a second ball Q, and that's got mass m kilograms. So we're not told what the mass is for definite, we're just told it's m. So going down on the object Q will be a force of its weight, which will be mg. So again, this may as well be labelled on, so Q has mass mg. So this is Q, has mass mg, and I suppose just for the sake of completion, we may as well do the same for P. We're told P's weight, oh sorry, I do apologise, I mean Q's mass is 0.2 g. So I'm going to label on here that's 0.2 g as well. And again, like I mentioned, for completeness, I'm just going to do model on the reaction force from the table on P, which will obviously be exactly the same as 0.2 g, because there's no vertical motion here. So, as well, of course, we need to always remember the tension forces, so tension acting that way on P and acting upwards relative to Q. And Q is above the ground, 1.2 above, and it's accelerating downwards at 1.9 meters per second. So again, just add it all in as much as you can. So acceleration's down 1.9 meters per second squared. So now we're pretty much ready to go and tackle this one. So using this model, find the tension in the rope. So what we need to do here is consider separately P and Q. So just considering P. Now P is going to accelerate horizontally. So the force in total horizontally going to the right for P is going to be the tension minus 1.5. So you can say this is T minus 1.5 equals the mass of P multiplied by the acceleration of P. That's going to be 0.2 multiplied by the acceleration. I'm wrong again. I thought we had to consider two particles separately. We don't. It's easier than that because we're told what the acceleration is. So we're told this acceleration is 1.9. So what we can do, we can add in this, simplify it, and then we're good to just work out what T is, just a simple rearrangement. So therefore t is going to be 1.5 plus whatever 0.2 multiplied by 1.9 is. So if we do this, we get 1.5 plus 0.2 times by 1.9, 1.88. So the tension is 1.88 newtons. For part B, we need to find the mass m of Q. So Q has mass m. So just considering Q now, we've done P. Let's consider now Q. So Q is going to accelerate vertically downwards. And so the force acting on Q downwards is mg. Resisting it is the tension, which we now know is 1.88. And that'll now equal the mass of Q multiplied by the acceleration of Q. The mass of Q is m, the acceleration of Q is the same as the acceleration of the whole system, which is 1.9. So again, now we've worked out the tension is 1.88, we're good to go. So, because we have an m at both sides, what we need to do is get all the m's together. So if I rearrange this, we have mg minus 1.9m equals 1.88. Factorise out an m brackets g minus 1.9, that's going to equal 1.88, and divide through by this g minus 1.9. So m is going to be 1.88 divided by g minus 1.9. So if we do this, we're going to get 1.88 at the top, and that's going to be divided by g, which is 9.8, minus 1.9, 34 over 395, which as a approximate decimal, 0.238 kilograms, so about 238 grams essentially. But in SI units, kilograms is the standard unit for mass. Leave it in kilograms, 0.238 kilograms. Now part C says a time after release for Q to hit the ground. Well, Q will hit the ground after 1.2 meters. Until it hits the ground, this system can be considered as having this constant acceleration of 1.9. So this is going to be a SUVAT type question. So the displacement of Q until it hits the ground is going to be 1.2 from here. The initial velocity is 0 because it's released from rest. I'll highlight that as well because I didn't highlight that one. Yes, system's released from rest. So because of that, U is 0. The final velocity, we don't know, and in fact we don't need to know it, so I'm going to put a cross by that one. The acceleration of the system, we're told in the question, is 1.9. And of course for time, well, the time is what we're trying to find out right now, so I'm just going to call time t. Then from this we can work out which one we need to use, which SUVAT formula. It's one which doesn't involve v and doesn't rely on v at all. Again, it seems to be S equals ut plus half at squared. It's crazy how much this one comes up. So plug everything in. 1.2. U is 0, so ut is also 0. So you're going to have half times 1.9 times t squared. So I'm just going to neaten this up a bit. So half multiplied by 1.9. What's half of 1.9? It's 0.95. So therefore, this can be rearranged. So t squared will be 1.2 divided by 0.5, sorry, 0.95. So to get t on its own, we square root all of this to find what it's going to be. So we're going to square root 1.2 over 0.95, and we get approximately 1.12 seconds to three significant figures. So just over a second it'll hit the ground. And if you think about it, that is reasonable, because 1.2 is about 1 metre. That's not particularly high at all, really. So next up, part D. State one assumption of the model which will affect the accuracy of your answers to parts A and B. So how could the mass have been affected, the calculation of the mass, and the tension in the rope? Well, there's two main things that could be considered. So one assumption is we've assumed the weight of the rope to be 0. We've not considered the rate of this rope at all. Or we could also have said here, in terms of working out the tension, the resistance on P is constant. Okay, so actually the friction may well change. It might not be 1.5 at all once it starts to slow down, for example. Or when it speeds up, the friction might become greater than 1.5. So that's an assumption. But I think the main one is probably the first one to put down, the rate of the rope, we're assuming it to be 0. And so that may have affected the calculation for the mass of Q had we used a non-zero mass for this rope. But anyway, for mechanics, we do use assumptions and simplifications to make life easier on ourselves. So this is standard, and that's fine. So that'll be a 1-mark question, probably. One assumption, 1 mark. Just write down any reasonable assumption. Typically, it's that these strings and ropes are assumed to have negligible mass. Okay, so that's all from me. It's now finally, after all that, over to you. So if you turn to page 175, exercise 10F, in the year 1 Stats and Mechanics book, and try all those exercises, all those questions within the exercise. That's enough to be going on with for now. And with practice, these do become easier. I do think these questions can be quite tricky at the best of times. Even more reason for you to practice and have a go. If you get stuck, you know what to do. Check the answers, ask classmates. If that doesn't come up with any use, ask me, either in class, on email, or in the comments section of this video you happen to be watching. Thanks for getting to the end of this video. It might have been quite a long one to get through. Take care, and I'll see you all soon. Thank you.